Come on, everybody! Walking Mr. Sunshine. Na 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 na, Katamari on the swing. Na 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 na, Katamari on the swing. 今始まるよ君と僕の未体験アドベンチャー。スカイ照らしてよ。お日様は僕らのスポットライトさ。おスマイル聞こえるよ。都会のシャレたスイングビート踊ろうよ。Dance, dance, dance くるくる回る雲を突き抜けて君と転がりたい愛のかけらを集め空に向かれよ Yeah, how can miss the sunshineなななななななな僕らのシンフォニーななななななななはじけるファンタジー今始まるよ君と僕の未体験アドベンチャー。照らしてよ星空は僕らのブラックライトさタキシードシャレして踊ろう僕らのリズムで流行りのステップステップステップ風切って回る視線は国づけさ君と固まりたい二人は運命の中に巻き込まれたんだ Oh yeah, how can miss the sunshine なななななななな Talk like destiny ななななななななやっぱり I love you
Hi everybody, welcome back to Chem 121. We'll just pan this out here. There we go. Exams are over! Hooray! We don't have to deal with that again for 5 more weeks, and then we have to deal with it twice. Because midterm number 2 and the final are practically on top of each other. So hopefully you did well. The average scores were pretty good. I try and shoot for a C average because that's how college works, basically, and if we get there, that is great, as far as I'm concerned. If you scored well on the exam, congratulations, your hard work is paying off. I'm very happy. If you did not score as well as you would have liked, I do want to encourage you to look into the online tutoring center and participating more in the Discord. I think we could probably have more questions in the Discord. Like, I'm surprised that I'm not answering as many questions as I guess I think that I would be, considering that it's midterms. So please use those resources. Also, email me, those sorts of things. Remember, I am a resource. Don't think that you're imposing on me. This is literally my job. You are paying tuition so that I can help you. Please don't forget that, okay? I'm more than happy to help you, but you do have to ask, because I'm not psychic. As much as I try. I've tried taking levels in Psionicist, but telekinesis through the internet, not telekinesis. See, I can't get the terms right. That's why I'm so bad at it. But I can't read your mind, is what I'm trying to say. I'm not clairvoyant. So if you need my help, you got to come to me. Okay. Agenda stuff. Quiz number 5 is due this week. It's due on Tuesday. Make sure you get that in before the deadline. We're going to talk about lab number 3 this week on Tuesday. I have not finished grading the labs yet. I'm like 40% done. I was going to do that last night and try and do more labs, make some progress, and then I realized, I need to release exam scores, and that takes like an hour to prepare. So I did that, and then by the time I was finished with that, I didn't want to work anymore because it was Sunday. It was Sunday at 10 p.m. So, you know. Okay, we're going to do Chapter 6 today. Chapter 6 is the return of math. You will need a calculator, and you will need ptable.com. Let me get the link for ptable.com. We'll throw it in the chat here so that you have it, just in case you haven't bookmarked it already. Oh, there's a cat here. I just bonked the cat in the face on accident because I didn't know he was there. It's not Maya. This is Kresnik. I don't know if he'll say hi. You want to say hi? Meow? Meow? No? Okay. He just wants me to pet him. I know I fed you this morning, so you're not... He's trying to be mischievous. We are going to do math, so you'll need a calculator. If you don't have a calculator handy, I will give you Wolfram Alpha, which I believe we introduced earlier in the quarter. That's just an online, like, you could type something in there and it will do a calculation for you and show you what it tried to do. In the off chance that I didn't actually introduce that to you. So, all right. So let's go ahead and get started and introduce this concept of this special unit that we use in chemistry. It's called the mole. Now, you might think that mole is short for molecule, and that's where the abbreviation came from. And honestly, I thought that for years, too. Turns out that mole is Latin, and the term mole actually means small pile of stuff. And that's trivia just for you. But it's also a good way to conceptualize what we're going to talk about. We're literally talking about piles of stuff, where the amount of stuff in the pile is going to be a fixed, specific number that we're going to come back to. The second thing that we need to talk about is how to figure out how much stuff weighs if that stuff is a formula. So, in Chapter 3, we assigned masses to the elements on the periodic table in AMU. And that was just whatever the number was for the mass number, right? So, like, chlorine 37 would be 37 AMU. And I could write that down right here. So if I had something like this... Like, if I had a single atom of chlorine 37, this is how much it would weigh. Because that's the mass number. Remember that the mass number is the number of protons plus the number of neutrons. But then we said, well, okay, if we're going to look at chlorine on the periodic table, it looks like something like this, right? and that this number represented the average mass of the sample of chlorine that we acquire in AMU. What that means is that there's not only one isotope that weighs 37. There are other isotopes out there. In particular, there's an isotope of chlorine that weighs 35. And on average, if you just took a random sample of chlorine, each one would weigh, on average, 35.453. Now, do any of them weigh that amount? No. They only weigh 35 or 37, right? Because that's what their mass numbers could be for the individual isotopes of the atoms. But on average, they would weigh that, 35.453 AMU. So if we made a bunch of it, it would be like they all weighed 35.453, even though they don't. Well, now what we're going to do is we're going to start making compounds out of these. So I'm going to grab sodium here. There's what sodium looks like. So if I wanted to weigh a sodium atom on average, it would weigh 22.990. So what do you think if I wanted to weigh sodium chloride, the ionic compound, what do you think I would do to calculate its mass in atomic mass units? And hopefully seeing me write them next to each other, you are thinking, oh, well, duh, you just add them together, and that's totally what you do. So that's what we're going to be doing. We're going to add numbers on the periodic table together on the bottom of the boxes of each element. That is in our formula. And if we have multiple of them, we'll just multiply by like 2 or 3 or whatever it is that we need to do. So if this number down here at the bottom is called the atomic mass, which represents our average here, then the formula mass is going to be all of the average masses summed together. So for instance, if I have this formula, SNF2, and I wanted to figure out what does it weigh, I just would go to the periodic table, and I basically am like, it's like I'm going shopping, right? Tin has a mass of 118.71, so I'll pick up one of those. And I need 2 fluorines, so I'll pick up 2 of those. What was the total cost in terms of mass, I guess you could say. And so you just add these up together, and you do have to worry about Sig Figs, so be careful. Since we're doing addition here, and our addition goes to the hundredths place, there's 2 decimal places, right? So if these lined up, it would line up like that. Oops, I wrote the wrong letter there. Now, for Sig Figs, we're going to actually do a shortcut. Because you're going to be doing this so often, and you don't want to write this out vertically all the time. What I'm going to suggest to you is that whenever you calculate the formula mass, do at least 2 decimal places, and you'll be fine. So, for instance, if you have a periodic table that has tons and tons of numbers, and you're like, oh man, every time I do this, my sig figs are different, because not every periodic table has the same numbers. I believe that p-table goes to 3 decimal places or something like that. Yeah. In fact, it depends on what element you're looking at. They all kind of go to different numbers of sig figs, right? Just use 2 decimal places, and you'll be okay. Now, some elements don't have 2 decimal places. For instance, like lead or something. It only has 1 decimal place. That's okay. Use up to 2, if possible, and more if you want. And then when you're done and you do all the addition, just round down to 2. So, let's do another example here. So, I'm going to look up all the molar masses of these elements on the periodic table that I have here. So, I have a nitrogen, which my periodic table says is this. Excuse me. And then how many nitrogen are there present? Well, I've got this 2 on the outside, so I got 2 of this whole thing, right? So there must be 2. And then I've got hydrogen here. And I've got 4 of those. And then I've got carbon, which is just this. And I don't have to multiply that, so I'm just going to bring it straight over. And then I got oxygen, so this is carbon. And then this will be oxygen. We just have arrows going everywhere. It's like a football diagram. That's appropriate because the superb owl is approaching, isn't it? And it's convenient for me that I lined all these up vertically, but remember what I just said. Just punch in your calculator and then chop off down to 2 decimal places, and that's fine. So I'm punching this all in the calculator, and what I got was 60.056. If I worry about Sig Figs, because I'm okay to go into this decimal place. But at the end of the day, I'm just going to report, well, I'm going to report the wrong answer if I do that. So there we go. And that's good enough. And the reason that I'm going to accept that is good enough is because, again, I don't know what periodic table you're using. If your periodic table didn't have these last digits here, and you had to round to that spot anyway, I have to program Canvas to accept your answer, right? So I can't make it too precise that it excludes answers from people who have different periodic tables. So that's not a thing that I want to do. Also, I don't really care if you round to the wrong number of sig figs because you had too many. If you have too few, that's different. But if you have too many in this particular instance, it won't affect your calculation, so don't worry about it. So just as long as you have 2 decimal places, you're going to be okay. Because as you can probably surmise, this is very basic, which means we're probably going to do it 90 billion times. And that's exactly what we're going to do. So, oops. All right. Now, what I want you to do is I want you to figure out the formula weight of these molecules that I've put on the screen. Some of them are ionic compounds, so they're more formula units, but I want you to practice doing calculations with this in your calculator, and then I'm going to show you an even easier way when I introduce something for it. Okay? And then I think there are homework practice here. Yeah. So I'm going to give you like 3 minutes to do this, and then we'll go over the answers in my Cheater McCheaterson way. So I'll see you in a bit. All right, one more minute. Once you have figured out any of these atomic masses, go ahead and print your result in the chat. We'll go over the answers shortly. All right, let's go over the answers here, and I'm going to show you how we're going to do that. So, I'm going to paste this link in here for you, and then we'll put that on the screen. So, this is actually a water quality website, I believe. Like, they do treatment and analysis. But what they also have are a bunch of calculators for chemistry, and I use them a lot, and for some reason this is not showing up. So why can you not find this? There we go. All right, so this is Lentech. We'll put Lentech up there at the top so you can see it. And what Lentech does, we don't really need this site over here, is it's a molecular weight calculator. So all you have to do is type in the formula of whatever it is you're working on. Let's have all the formulas on the screen so I could just do this. And so we'll go ALCL3. Make sure you type in L's instead of I's because you'll get a different result. And there you go. So the first one should weigh 133.34. And now you never have to use your calculator again. And now you also know why I said 2 decimal places, right? Because that's what Lentech does. So now that you know how to do this, you don't have to waste your time calculating it again because it's a very basic concept, right? So BA parentheses OH parentheses 2, that one weighs 171.34. And then we have parentheses NH4 parentheses 3 PO4. And you just type them in exactly how your formula shows. So that one's 149.09. And then finally P4O10, enter, 283.89. So there's your answers for that. And the speedy way to do this. Now, why did I make you do it the long way? Because you had to do it the long way to appreciate the short way, right? That's how it's true with everything. You gotta understand the fundamentals before I can give you the shortcut. I don't put you behind the wheel of a car and say, good luck, we're all counting on you. No, we give you like hours and hours and hours of training classes, and you have to pass a test and stuff like that. So the same thing with chemistry, right? Same thing with anything, really. So now that you know how to do it, you don't have to do it the long way ever again. So there you go. We're going to use that, so keep Lentech handy for any problems that will involve a molar mass, which there's going to be quite a few of them because we're going to use them in just a second. Okay, now that we have done this first initial thing of how much do formulas weigh, let's introduce this new unit. So this is called the mole. Remember that the mole is basically Latin for a pile of things. How many things are in a mole? Well, let's put that on the screen here. 1 mole of things has been defined by us as this number of things, 6.022 times 10 to the 23 things. And this is called a mole. Now, that is an oddly specific number, right? Why not just 6 times 10 to the 23? Why 6.022? And the answer is because, one, this is not an exact number. This is a counted amount based on a calculation and an experiment. And two, we need to have as many sig figs as we can for our calculations. There is a third reason, and we'll get to that in just a little bit. But if I take a sample of what I want to call a mole, it will have this many objects in it. Now, a mole is just a denomination like any other counted denomination. For example, if you are a couple, then that implies that it's you and one other person, right? Because you're a couple. A couple is two. If you go to the bakery and you buy a dozen donuts, then you are getting 12 donuts, or 13 if they're a baker's dozen. So, like, dozen is kind of a weird example because it's not clear. But the word dozen represents either 12 or 13, in the same way that a mole represents 6.022 times 10 to the 23. Now, because atoms are so tiny, we have to have this ginormous number to use a reasonable amount. So the reasonable amount we've decided upon for our reference here is that 12 grams of carbon, specifically carbon 12, is our reference. In that, there are Avogadro's number of atoms. And you might be thinking, oh, wait a second, 12 for carbon 12, that's awful convenient. And yeah, it is. We've chosen 12 for that reason, because this sample that was abundant when they did this experiment, I guess, was the reference point. And we'll get to that relationship in just a little bit. But for now, what we want to do... the name for this, by the way, is called Avogadro's number, and by the end of this class, I almost can guarantee that you will have memorized this number. Just because it's catchy, I guess? I don't know. Everybody knows Avogadro's number. I think I even put a comic up about it. Did I do that? No, I didn't. I guess not. That's okay. Sorry, I'm trying to find where I'm at. There we go. Now, the secret third reason that why we need Avogadro's number to be what it is because if 1 mole equals Avogadro's number, then the following is true. So the AMU, the mole, and the gram are all actually very carefully defined around each other, such that 1 atomic mass unit is the same as 1 gram per mole. In other words, if I have something that weighs 1 AMU, like hydrogen, then its mass per mole would be 1 gram. If I got a mole of hydrogen, it would weigh 1 gram. If I have something that weighs 12 AMU, like carbon 12, then it would weigh 12 grams per mole. And so this is called the molar mass. In grams per mole. And this number is on the periodic table. So that number at the bottom that we were writing in AMU, you would just cross out where it says AMU and write grams per mole now, because these are the same unit. We have defined them as such. And that's why Avogadro's number is a weird number. We defined the other 2 units and then solved for Avogadro's number, whatever it turned up to be. Now, what this means is that for any given thing on the periodic table, we can get a bunch of conversions out of it based on these definitions that we have constructed. So what I'm going to do is I'm going to do this. But I'm going to capture this over here in the corner. We're just going to put that over to the side here. And so what this means is that we have 3 relationships that we can put together. We have grams per mole, And then we have atoms per mole. And then we could also do grams equals some number of atoms. These two conversions up on the top are going to be the most important. But let's show how we can get these relationships, where x and y are just whatever number they end up being. They're not all going to be the same number, but we're going to make relationships out of these. So the first one we're going to do is the standard definition. How many atoms are there in a mole? There are always Avogadro's number per mole. So regardless of what these could be, the rest of this equation will always be true. There will always be Avogadro's number of things in a mole, because that's a definition. That definition is always going to be true no matter what. So if you are ever doing a conversion of, oh, I have this many moles, how many atoms are there? Always remember this conversion and you can use it. The second conversion is going to be, I just realized that my iron is in the way here. Let's just put this over here. The second conversion that we're going to use is grams per mole. So 1 mole of iron is whatever number of grams there is per mole from the periodic table. And we get that from the atomic weight, or the atomic mass at the bottom. So that would be 55.845 grams of iron. So there are that many grams of iron in 1 mole. And then if something equals 1 mole and something else equals 1 mole, then those two somethings must equal each other. But honestly, we're not going to use this conversion down at the bottom very often. These two right here are much more important. And you'll see why in just a little bit. Now again, this number right here is from the periodic table. And so that's going to be unique depending on whatever this is. So if I put something else there, so I change iron to, say, chlorine, I also have to change the number. But for the ones up at the top, I can change the iron in the relationship between Avogadro's number and a mole, and those numbers will stay the same. I can just change the atom to whatever I want it to be. Sorry, I gotta drink more water. Stay hydrated. Alright, so there are relationships that we have here. And because we have relationships shown that are equality, sorry, I'm just going to reformat this before I close it. Because I have relationships that are shown as an equality, I can make those into things like this. So I could say 55.845 grams of iron over 1 mole of iron. And I can already see the rolling of eyes in the background of the astral plane as 50 collective Chem 121 students said, oh, fuck, do I have to do this shit again? Yeah, you do. That's what we're doing in Chapter 6 here. The good news is this is the hardest part of the math. If you can make it here, you can make it anywhere in Chem 121. So let's get through it together. We'll be okay. So let's do some examples before I set you off on your own to try a few problems. So this first example here, what is the mass of 2.6 moles of sulfur? And so what we're going to do is we're going to write down the amount that we're starting with. And then I need to make a little blueprint here. What do I want to turn moles of sulfur into? Well, it's giving me a mass as my answer. So I'm going to say grams of sulfur. And now I need a relationship between moles of sulfur and grams of sulfur so that when I cancel out my units, I get what I want. And so that means that we're going to have to look up the mass of an element on the periodic table, because that number of grams will equal a mole. Well, fortunately, I still have the periodic table here. So what number do I write down? Hopefully you've written it down, because it's the number at the bottom, 32.06, which I now have on the screen here. There are that many grams per mole. And then I just copy the units down that are left over and report my answer. So now we'll multiply the numbers together. And I got 83.356 grams of sulfur. And now I have to do Sig Figs, because Sig Figs are the last thing that we do, right? So this number is 2 Sig Figs. This number is 4 Sig Figs. Ones are exact, so we ignore them. So my answer should have 2 Sig Figs. So I'm going to report these 2 Sig Figs. You don't actually need this decimal point. I just tapped the pen on the thing on accident. Oh no, cats are fighting. Stop that. I might have to address this in a second here. If I can hear them in the distance. They're hissing and yowling. All right, and so I have a little example of that right here. So now that I've done one, I want you to try this one. How many sulfur atoms are in this mass? I'm going to break up the cat fight that is happening in my hallway. So I'll be right back. Go ahead and give this a try. All right, I'm back. One cat was upset because the other cat was sitting on the paper bag that he likes. And he didn't want to share. Because of course they were. I'm going to give you 1 or 2 more minutes to finish this problem. And if you get an answer, go ahead and type it in the chat. We'll go over the results in just a second. All right, let's go over the result here. So I need a relationship between grams of sulfur and atoms of sulfur. And so I give you a mass to start. And then I need to do something like this. And this will be like the one time we use this conversion. Because there will be a reason that we don't want to go directly from grams to atoms later on. That we're going to go through moles in the middle. And we'll discuss that in the next section. So, how many grams of sulfur per number of atoms? Well, I know that there are this many grams of sulfur per mole, right? So if I get my periodic table back up here, there's sulfur. It's 32.06 still. And so this is the amount in 1 mole, right? But 1 mole is also Avogadro's number of atoms. So we don't need this middle point here if we don't want to write that down. But now we have to type this in the calculator. And this is where things get a little bit tricky. So what I'm going to do is I'm actually going to call up Wolfram Alpha here. We're going to try and enter this into Wolfram Alpha. And we'll just shove it down here for now. So I'm going to type this in. So we've got 49.1 times 6.022 times 10 to the 23. Oops. Divided by 32.06. Hopefully that showed up on the screen. Yeah, it looks like it did. Okay. And then all you do is you just hit enter, and it will process it for you. And so this is what it thinks that we asked it to do, which is close enough, really. And this is the result that it got to like 60 billion sig figs. So 9.22 times 10 to the 23 is what it gave us. So we're going to write that down as our result. And then our units are atoms of sulfur. So there you go. So we can do dimensional analysis using any 2 units, even these new units that are kind of weird and bizarre to us. So we'll put that on the screen here too. I had 9.21 on my calculation. That's fine. I used a different periodic table mass. All right. So now what I want you to do is try this one. How many moles are in 71.25 grams of sulfur? I'll give you like 3 or 4 minutes to try this. Remember, write out the relationship of what you have and what you're trying to figure out. So in this case, I'm giving you grams. What unit are you trying to go to? Write out the relationship, and then set up the equation so that the units cancel out. We'll go over the answer in just a second. All right, one more minute. We'll go over the answer here. All right. So just like before, we'll set up our relationship. I'm always using sulfur in these examples because I want to keep a consistent number involved so that we get used to what goes where. And so our relationship is going to be grams turns into moles. So what relationship do we know for grams to moles? Well, we know that the periodic table has a number of grams in 1 mole. So I'll write down how many grams I was given. And then we'll turn grams into moles. Like that. And then we go to the periodic table, which I have to find again. It's on Lentech. That's not what I want. I want this. There we go. So sulfur, again, 32.06 grams per mole. So we'll write that down. 32.06 grams per mole. And then we'll do the division. 71.25 divided by 32.06 is a bunch of 2s, it looks like. And then how many Sig Figs does our answer have? Well, this is 4 Sig Figs. And so does this one. So our answer should as well. All right. There's my answer there. So what I'm going to do is, here are some practice problems to start on. I'm going to leave this on the screen for just a second so you can pause the video if you want to, but we are going to take our break here. If you want to work on these, I'm going to give you time after the break. But for now, we're going to just take a breather and relax to some bizarre space music from the Katamari soundtrack. If I can find the correct track here. Yeah, there we go. Okay. We'll see everybody in just a little bit. Don't worry, your speakers are not glitching out. It's just the song.
day with rain あなたと Every day with rain 二人で Every day with rain 固めて I'm gonna wake up with a smile I feel love it like a child Believe あなただけ We are all real That is my loving 雨の中で踊る Come like a journey to find a happiness そう愛の香り Come to me Hear the wind blows 世界を Hear the wind blows 二人で Hear the wind blows 固める I'm gonna wake up with a smile I feel love it like
And we're back. Hope everyone had a good break. Now it's time to get back to work and do these problems. Do these 3 questions that are on the board, and we'll go over the answers in just a little bit. So, see you then. I'm going to give 1 or 2 more minutes, and then we'll go over the answers here. All right, let's go over the answers here. So I'm going to go over to this screen. Where did my pen go? There it is. All right. And then I need to capture... Where is my P table? There it is. And that's a little big. We'll just do that for now. All right, so I'm working with helium, so let's get helium on the screen in case we need it. There's helium. All right. What is the mass of helium in a balloon containing 1.7 moles of helium? Oh, this is great. I'm going to draw with the select tool. There we go. All right. I need to go from moles of helium to a mass because it's asking me for a mass. Well, mass is in grams. And I need these units to cancel out. So we'll put moles on the bottom and grams on the top. And we're all set with units. Now I just need a relationship that uses the units correctly. How many grams are in a mole? Well, according to my periodic table over there, 4.0026. I don't need all those digits, but we'll write them down anyway. So we're going to multiply these numbers together, and for 2 Sig Figs, I get 6.8 grams of helium. This would actually be a very large balloon. This would be like 30 liters of a balloon. But that 30 liters would only contain 6.8 grams, because helium is that light. All right, that's the first one. Let's look at the second one. How many atoms are in a sample of 34 grams of sodium? So over here, we'll click on sodium. Boop, there you go. And let's do the same thing. So I've got 34 grams of sodium. And I need to go from grams of sodium to atoms of sodium. What relationship do I know that does that? Well, let me do the units first so we can get it all canceled out. And then we need to look at numbers. So for this problem, for sodium, there are 22.990 grams of sodium per mole. And then in 1 mole, there are Avogadro's number of atoms. And then we just don't need this part anymore. And then punch it all in the calculator. 34 times 6.022 times 10 to the 23 divided by 22.990. If you have numbers on the that you're dividing on the bottom, putting parentheses around them is generally a safe bet. We're going to see some instances of that where that can give you the wrong answer if you're not careful later on. So there's how many atoms of sodium would be in that sample of 34 grams. And then finally, how many moles of lead are in a lead ingot weighing 805 grams? This is not a very big ingot, but that's okay. I gotta go click on lead here. So there's lead. All right. You'll notice that lead only has 1 decimal place. That's normal. All right, so I got my lead here, and I want to go from grams of lead to moles of lead. So let me set up my units here. And now that I have this, how many grams are there per mole? Well, according to the periodic table, 207.2. So how many moles of lead are in this sample? About 3.89 of them. There you go. I put a little doohickey on my B here. All right, that's how we do these basic calculations between grams, moles, and number of atoms. That's going to be very important for us to serve as our foundation to do the more advanced calculations that we're going to be seeing in just a little bit. So there's the first homework set, 5 through 20. There's a 1 through 4 earlier that's like, let's add these numbers together, but this is the real important ones. So make sure you do this practice. And let me know if you have any questions. All right. The next thing that we're going to do is we're going to take formulas and involve them with these calculations. So what we were doing before, we were just picking random elements off the periodic table. How many grams of helium are in this balloon if this is how many moles are in there? How many grams of lead are there in this number of moles? That sort of thing. Now we're going to start using molecules, but also looking at different parts of them. So let's do that. So the first thing that we want to look at is what is meant by a formula when I write this. Now, for any given formula, you can write a statement that tells me what's in it, right? In 1 molecule of P2O5, there are 2 phosphorus and 5 oxygen atoms. That sentence makes sense, right? I'm interpreting these numbers, the coefficients, and then representing them as words. So what I'm going to do now is I'm going to try and make an equation out of that. So 1 molecule of P2O5 has 2 phosphorus atoms and 5 oxygen atoms. So that's true. For this molecule, I could write this statement, right? For 1 molecule of P2O5, there are 2 phosphorus atoms and 5 oxygen atoms. Now, if I only want to look at one part of it, so let's say that I just want to look at this part. That statement would be true, right? So if I did something like this and I said, well, I'm going to hand you 59,800 molecules of P2O5, and I want you to tell me how many phosphorus atoms are in there. You would just say, oh, okay, well, molecules of P2O5 will cancel out here, and atoms of phosphorus will go there, and there's 2 atoms per molecule of phosphorus. And of course it would just be however many molecules you had times 2, because there's 2 right here, right? And so if I did that, it would be 119,600, which I'd then have to round to 3 Sig Figs, but you get the point, right? So you can use these conversions that we're making from the sentence just like we would use any conversion. Now, to make the conversions a little more practical, what we're going to do is we're going to do this. Because we don't want to work with individual molecules in calculations. That's too tedious. So what we're going to do is we're going to go like this. We're going to multiply by a mole to create a new relationship. Then we can just do our calculations with moles, right? So a mole times a molecule is a mole of molecules. And 2 atoms times a mole is 2 moles of atoms. Which we could just write like that. So in 1 mole of molecules, there are 2 moles of phosphorus atoms. And if I did the same thing down here, there would also be 5 moles of oxygen atoms. Which I'm just going to write like that because the mole atoms and mole are more or less the same thing. A mole is just a count of them, right? So now I have relationships that I can then use to do dimensional analysis. If I have 20 moles of P2O5, how many moles of oxygen are there? Well, it's 20 times 5, right? 100. And we can do that dimensional analysis now. So, using the formula, one big thing, which is the molecule itself, is going to be equal to that many moles of the little things. And I should say 1 mole of the big thing up here. You can think of this as like a Lego or like some sort of like structure that you could pull apart. So like if all these atoms were bonded together using like toothpicks or something, you could pull all the atoms off the toothpicks and then sort them. And you'd say, okay, well, here's a molecule. I pulled apart all the pieces. There were 2 phosphorus and 5 oxygen. So if I give you a mole of those, there you would presumably have 2 moles and 5 moles. All right. So that's going to be what we're going to work towards here. We're going to answer questions that are along the lines of this. How many moles are in this sample with this given formula? That's the wrong button. Good job, me. That's also the wrong button because I don't know what I'm doing. That's what I want. I never know if it's Control or Alt, and then for the first key there I hit Windows, because Windows is a helpful key, and I always hit it. My thinly veiled sarcasm there. So for this problem, I want to know how many moles of oxygen are in there. So I have moles of P2O5 to start, but I want to convert that to moles of oxygen. So first let's set up the units. I got to get rid of this thing to make this thing, so... Do I have a relationship that I can put for that? Well, sure I do, because I know that in one of the big molecule, there are this many of the little thing. And there you go. And so now I just multiply these together. Wow, what did I do to do that? That's not at all what I wanted. Oh, I removed it. Okay, there we go. No, that's also wrong. I, like, completely screwed everything up here. What have I done? Sorry, I messed up part of my thing. Now you can actually see this because it's not supposed to be over there. How do I resize this? That doesn't work. Sorry, I'm playing with something. Oh well, you'll be able to see my tools on the side that I'm using here now. That's okay. I accidentally clicked something and I broke everything. Story of my life, right? There you go. So that's how we do this. There are that many moles of oxygen in this many moles of P2O5. Now I could do the same thing for phosphorus if I wanted to. So just as an example, let's suppose that I wanted to instead solve for the number of moles of phosphorus instead. So this would change my question. I got to find the eraser tool. I don't know where anything is anymore now. So now we would be solving this problem instead, right? And then there are two of those. And so my answer for this one would be that. So the number that's going to be linked to the individual atom is going to come from the formula. That's how we're doing this. All right. Now, oftentimes we don't work with moles. So like here we're starting with moles and ending with moles. What we're going to eventually have to do is introduce grams into this, and we're going to have a longer calculation. But for now, let's just do these types of calculations. So I'm going to give you this problem, and I want you to type the answer in the chat. How many moles of carbon are there in 1.2 moles of this? Now, you might immediately just have a reaction to this and go, oh, that's the answer. And you're probably correct on it. But what I do want you to do is write out all the units. Okay, so make sure that you're setting up your units like I'm doing here. I don't just write all this out for the good of my health. I know how to do this, right? But the reason that I know how to do this is because I write out the units every time. And I actually do write out the units every time. And you should too. Just because we want to convey that you understand what's going on. Okay, so write the answer to this in the chat once you get it, and we'll go over the answers together in just a moment. All right, one more minute. We'll go over the answers. All right. So let's go back over here. We'll pull. Oops. All right. So we'll do the same thing. So I'm going to go from 1.2 moles of this molecule, whatever the heck this is. I don't know what it is. And I just want the carbon part out of it. So let's set up my unit so that they cancel out. And then in one of these big things, how many of the carbon are there? Well, there's 3. And there you go. Very good. That's the answer. All right, let's do another one here. I'm going to just scroll this down here. I'll give you a second to try this. Now, you'll notice that I didn't give you moles anymore to start. I gave you an amount of grams. Well, what do you know about grams? You could turn grams into moles by doing some sort of calculation. You might need something on the screen to help you. Well, not something, but you might need to use the periodic table and Lentex. So now we're going to start putting everything together here. And so that's what I want you to do. I want you to try to solve this question. How many moles of oxygen atoms are in this quantity that is a mass? So you have to do one extra step here. I'll leave you like 3 or 4 minutes to try it. Type your answer in the chat if you get it, and we'll go over it shortly. All right, one more minute. We'll go over the answer here. All right, let's go over the answer here. So we know how to do this second part here, right? So if I write down... We can do that part, because we've been doing that up above, right? But now we have to add in this part. Which means that if I have 144 grams of C3H6O3, in order to get to this for my answer, I'm going to have to go through this middle part, right? And if we can get an answer for here, then I can just do this, which we done before. And so these numbers are easy. There's in one of the big thing, there are 3 oxygen because of that number right there, yeah? But it's this middle part that we got to figure out. And remember how we can do that. How many grams are in a mole of anything? Well, if it was just one element, we'd write down the number off the periodic table. What if it's a bunch of elements? Well, then we go to Lentech and we type it in, right? So if I do this, which is now too tiny to see. So we'll type in C3H6O3. And it tells me that the mass is off the screen. You can't see it. There it is. 90.08. So in 1 mole of this thing, there are 90.08 grams of it, right? So if I do this calculation, I will have the number of moles of oxygen that are present. And that would be 144 times 3 divided by 90.08. And I get 4 point, looks like 80. So for these calculations, you're going to have to go do another step because grams will often be involved. It's very easy to weigh grams out. All right. So for the last example, what I want you to do is, oops, we'll put that on the screen here. So I want you to do, for this problem, I want you to tell me how many moles of each type of atom are in a 0.377 mole sample of deoxyribose. And then what I want you to do, as an extra problem, I want you to tell me how many grams of deoxyribose this is. So I'm going to have you go in both directions. I've given you the middle calculation, okay? So I want you to do that. Type your answers in the chat once you get them. We'll go over the results in like 5 minutes, and then we'll be done for the day. All right, see you in a bit. All right, one more minute. We'll go over the answers here. Feel free to type in anything you got in the chat. All right. So for this problem, what we're going to do is we are going to figure out how many moles of each type of atom there are in deoxyribose, and then figure out how many grams that is. So the first thing we need to do is write down that. And I'm going to just do this really quickly. I'm going to just go copy, and then we'll deal with that in a little bit. So the first one, we're going to do moles of, we'll do moles of carbon. So that those cancel out. And now I can just say in one of these there are 5 carbon, because that's what the formula is, right? And we'll just take that number and times it by 5. All right, great. We can do that. That's easy enough. Now let's go paste. And we'll do it again. But this time we'll go with hydrogen. And we'll do the same process, right? Except instead on the top we'll put moles of hydrogen, because that's what we're solving for. Sweet. Okay, cool. And then we'll do the same thing again, but this time we'll do it with oxygen. And you'll notice I'm writing it out every time, because that way it's clear, not just to me, because I'm not doing this for me, it's clear to other people, right? So you should also write out all the units every time. How many oxygens are in the molecule? So in one of these molecules there are 4 oxygens. And I'm not going to do that one in my head. There we go. And then the last problem that I asked you was how many grams is this? Well, guess what? You can also copy this. We don't need this mole here because we're going to do something different with it. But other than that, everything still works here. So now the last problem is I want to know how many grams this is. All right. And so how many grams are there in 1 mole? Well, it would just be whatever all of those atoms of the periodic table are added together. Or we could just go straight to Lentech, which I believe is still on my capture. So there. So we'll just type it in. So C5, that's 6, H10O4. And the mass of that is 134.13 grams per mole. So we'll write that down. Well, I don't have 1 mole, I have 0.377 moles, so we'll multiply those together. And I get 50.6 grams of deoxyribose. All right, so those have been several examples on types of calculations that we do for grams to moles. Now, you've seen that I can go back and forth between coefficient and molecules. So that's what we were doing up here for these. And you've seen that I can do grams per mole of what I start with. I could also do grams per mole with what I end with. So when we come back tomorrow, what we're going to be doing is we're going to be continuing this type of calculation. Very, very important. Everybody gets stuck in these types of calculations because they do this for the first day. And they're like, okay, I sort of get it. And then they don't do the homework. And then we come back tomorrow and nobody has any idea what's going on. So, strong advice. If you don't have plans for today and you have some time, sit down and do these homework exercises because it will seriously help you retain this stuff. And there they are on the board again if you want them. It will seriously help you retain this stuff, especially early on. If you just say, like, okay, that's it for me today, I'm going to see you tomorrow. We come back tomorrow and we continue using this, and you're like, oh, I don't know what to do. You're kind of screwing yourself over. So just earnest advice. That's really all I have for today. I do want to thank everybody for coming out to the lecture. Make sure that you get quiz number 5 in by Tuesday. That's when it's due. 1 extra day, 24-hour period if you need to turn that in afterwards. Yeah, I don't really have much else, so... yeah. Have a good night. Make sure you do some practice on this, and we'll continue Chapter 6 tomorrow. Take care.